Hi, so I want to tell a little bit of a story here. I've had this meter now sitting on my bench for, well, since November 2014. And there's a bit of a story behind it. Yes, it looks like just a cheap multimeter, the kind of thing that you don't want to use with high voltage. But yeah, that's exactly where the story begins. I was actually traveling to India. I hadn't got there yet. But when I did get there, I found this meter, and it was sitting around and nobody was using it. And I went to turn it on, and nothing. It doesn't do anything. And I asked about it. What's this meter that's sitting here that doesn't do anything, and why does it rattle on the inside? Well, then they proceeded to tell me the story about what had happened. And I'll just give you some background behind how this all transpired. We were installing some alternative energy hydrogen pumping equipment in India, and well, the company I was working for was, and it was running off of the Indian electrical grid. And I don't know if you know, but the Indian electrical grid, not the most reliable thing. Actually, that's the reason that they decided that they weren't going to rely entirely on the grid. They had a backup system that would automatically switch to of battery banks. Now, I don't know who designed the system that did the switching. That wasn't part of my scope. In fact, I never got to see the system, but I do know that it was causing some serious transients and dips in the voltage, and it just created all kinds of issues. And before I even got there, it was causing issues. And a very well-meaning salesperson at the company I was working for decided he was going to take some voltage measurements and see if he could catch one of the transients. Well, this was the only meter that he could get at the Indian bazaar that week. And I kid you not, that's exactly what it's like. You go to this bazaar, you see people will trade things for rupees, and this was the top of the line best one. We'll see here soon that this is still one of the worst meters that you can buy in the US, but things are different in India. So again, well-meaning person tried to take a voltage measurement, and it kind of backfired on him. Because a meter like this just doesn't have the kind of input protection or safety or CAT ratings that you would expect to see or that you need to see in order to take those kind of readings on an industrial scale. It was 415 volts AC, 3-phase, and it was directly on the incoming power coming from the utility company or wherever it came from in India. Magical clouds, I don't know. But, you know, it says here, I don't know if you can see that, it says 1000 volts DC, 750 volts AC. Yeah, okay. I don't think so. I mean, sure, maybe it'll handle that, but clearly any kind of transients that come across the line, it's not going to be able to handle that kind of overload. There's no overload protection on this meter. So let's take it apart and see what kind of damage was done, because the meter actually exploded while he was taking a measurement, and he's damn lucky, and I'm glad that he's okay, that it didn't do damage to his hand, that he could have been seriously injured, he could have been killed. It's very dangerous to do these kinds of things, taking measurements directly off of the mains incoming line without a CAT rating, category rating. That's exactly what category ratings are for. And in that instance, he should have had at least a category 3. Being that it's India, I really would have preferred to see a category 4, which is the highest rating, which tells you that it can withstand a certain voltage over a certain period of time above and beyond what its normal rating is. So again, let's tear this down. Let's see what kind of damage was done. I've been meaning to do that, and I think it's going to be a shocker. Okay, let's take this pile of crap apart. What we have here is a Unity, get my pointing device, Unity DT266 clamp meter. It's got the clamp up here that you could potentially clamp around your wire and measure the current. It goes up to 1000 amps AC, or, well, yeah, that's just going to be AC.
it's not going to be able to read DC. 1000 amps AC, I don't know, maybe. Although, you know, current, at least there's no contact there, so maybe that, maybe it could do that. How accurate it would be over time, it would be absolutely terrible. But anyway, let's take this thing apart. Since this thing's kind of junk, it's going to get the crappiest screwdriver that I have. Let's open the battery compartment here. Oh, yeah. Let's see if I can focus in on this here. Something terrible has happened here. You can see up towards here, in here, and in here, there's definitely some burn marks there. Oh my. Focus out here again. Sorry, I don't have automatic focus on this camera. It's actually just my SLR, and I'm working on getting a better video camera, but we'll have to make do with this for now. At least it does do 1080p. Another thing I'm noticing, and I don't know if it's as obvious in the video, but right here in this area, it looks like the plastic is actually melted or softened and dimpled in. I don't know if that's because of the cheap build quality nature of this product to begin with, or if that's something that happened after the fact. But we do definitely have some problems here. Look at that battery. And I forgot I actually had taken the battery out so that it wasn't sitting in circuit. But there is some definite charring on this battery. Never heard of a power leader brand, but I assume it's not much better than a golden power battery. Yeah. Definite charring around here, up here, some on the back there. Something really bad has happened to this meter. Now, I've taken the screws out, but I'm just curious to see what the battery reads. Now, I know this isn't a very valid test because you should be testing batteries in circuit under load, but I just want to see what it reads first. 9.9. That's actually higher than I would expect to see it. Let's put it in the meter and see if we can get any life out of it. If I remember right, though, this thing didn't work before. Moment of truth. Let's see if it works. Nah. It's got nothing. This is the worst feeling selector switch I have ever felt. You can probably see that this is so spongy that there are really no definite clicks here. There's a little bit, you can sort of feel it, but you can easily place it in many different positions between selections and not actually be, if you do it kind of fast, you can sort of hear some clicks, but it's just, it's nasty. It's not good. I've got the meter on the AC volts range. It's on right now. Let's measure the voltage on the battery and see if it's dropped. Oh, nice if I turn my meter on. Okay, let's see what we got here. And my leads are backwards, but 9.93, there is no load at all. So, as suspected, this meter is dead. Alright, let's get to it. We'll take this thing apart. See what we got going on here. Looks like it's... Oh, this came out. I wonder if that's why the switch feels so spongy. That looks like it was one of the ball bearings. Oh my. Yeah, there's quite a bit of blackness and little tiny particles of things in here, all throughout the plastic. It kind of shows up in the LCD as an unevenness. and it's not really easy to see, but here, right about here on the spring, there's a lot of charring and blackness. Let's see if I can sort of scrape it off, but not really. But this is where things really get bad. Like I said over and over, clearly something really horrible has happened here. There's some serious charring here, and it's clear that's where all this soot and smoke have come from. It's some over here too. It looks like there was a resistor here that got the ass blown out of it, and something here, probably resistor or maybe this capacitor. It doesn't look like it. Oh, I see. This trace got blown out. I don't think that would make all this soot. Maybe if there was enough arcing, it could have charred and vaporized the solder mask on that. So, wow, some serious energy there. Let's get this little piece of shit buzzer off of there. It's pretty interesting to see what might have happened here. So, clearly just a chip on board solution here. That is your absolute cheapest method. You'll find it in really low-end electronics. What they have is the actual bare die sitting underneath there and bonded directly to the board, and then they just put a blob of epoxy over it to protect the die. But yeah, it looks like maybe a trace here got blown out, and there. It looks relatively okay up here. We've got some melt package diodes here. A little unusual. You don't see those a lot anymore. There's your crappy hold button. It works, but not very good. And look at your input jacks. Oh, terrible. They're split for one, which I'm not a huge fan of, but there's like just these little straps going over there, and it's just horrible. Yeah, I mean, I guess what do you expect? Let me get this board out here, flip it around, and see what damage might be on the other side. Well, aside from a little bit of blackness here on the back of the LCD there, and here's your zebra strip that gets all the connections across. Yeah, cheap little thing there. Aside from that, this looks okay. I mean, there's a little bit of soot and blackness. You can see some more here, but you know, actually these contacts, I mean, they're crappy contacts, but they don't look like they've been particularly damaged from arc flash, anything like that. But here's where things start to look really, really bad. Uh-oh. Yeah. Clearly, a lot of these traces were blown out. And these are your traces for your selector switch that mates up with these contacts here onto this surface. As you rotate it, it selects to different ranges and whatnot. And yeah, there's some serious blackening there. Obviously it arced over between these because there's really not much creepage distance between these on the surface of the board. Remember I talked about leakage in a previous video where you have guard traces to protect from surface leakage on the board. In this case, it's called creepage. You don't want, it's a creepage distance. So the further you put these things apart from each other, the less likely that the insulation across the solder mask is going to break down and it'll arc over. But we had some seriously high voltages here, so whatever that transient spike was, we don't know what its magnitude was, but we do know that it was high enough to be able to arc over across these gaps, and you had some carbonization there. And the bad part is now, if you were to go and measure anything, or try to measure anything, assuming that our main chipset wasn't blown, which of course it is, then, you know, you'd have to worry about it arcing across these tracks, because once it carbonizes like this, it becomes a lower resistance path, and it's going to try and always take that path of least resistance across that carbonization. So that would not work well. I don't know what's going on here. Let me get a closer look. Yeah, that's just this white stuff you see here. That's flux residue. It's just It's a crummy board. We have a couple little trimmer pots up here. Don't know what I'm adjusting, but doesn't matter. Look at this switch here. It's only halfway on the board. They couldn't get an SP-DT. They could only get a DP-DT. That's single pole, double throw. The one that's actually on here is a double pole, double throw, because you've got 1-2 poles this way, and then double throw. You can throw the switch one way or the other. So, yeah, that's about it for this thing. You know, a couple wires go over to our crappy little clamp here. You know, not sure how good any of this would be. Oh, I didn't notice this before. Look at the buzzer. That white surface of the buzzer, you can really see where it got some carbon on there. Focus in on that. Wow. Yeah, so anyway, here is the reason that you want to have input protection on your multimeter. This has no input protection to speak of. There's nothing here. The clearance distances, the creepage distances, none of them are there. This would not pass any kind of certification for safety. So when it comes to measuring high voltages, get a quality meter. I can't say it enough. If you're just working on the bench and using isolated power supplies, 5 volts, 15 volts, DC, something like that, yeah, by all means, use a crappy meter. But even then, it's not going to be accurate. It's going to drift over time, and you're just not going to have measurement confidence. And that's something that you want to have. What's the point of a meter if it's not accurate? And even then, long-term reliability, is the thing going to fail? You don't know. It's better off just buy a more expensive meter if you have the means to do so. For safety's sake, if you're working on high voltage mains, you have to, as far as I'm concerned, you have to, for your own safety, get a category 3 or a category 4 rated meter. I can't recommend that enough. If you don't, then you do so at your own risk. So what does a proper safe meter look like? Well, let's just use the example of my Fluke 179. It's got category 3 down here, rated to 1000 volts, and category 4 rated to 600 volts. And these categories, again, what these mean, as the number goes up from 1 to 4, it's going to allow a longer duration and a higher voltage level spike, what's known in the industry as a transient. So if you're measuring mains voltage, what comes out of the wall, or even more importantly in an industrial scale where it's on mains power transformers outside on the pole, then you're going to have spikes in your power from lightning storms or just spikes from the generators, back EMF from generators. You're going to have spikes. It's not going to be that clean of power. It gets cleaned up as it goes along and hits your substation. So what this does is that protects you from those spikes. Sure, it's going to probably still destroy your meter, but you get to keep your hand. So I think it's a pretty fair trade. Anyway, let's take this apart, and I want to show you what a properly designed meter looks like as far as protection. And you notice right off the bat, this groove here, you can see how it steps down into a shoulder, and then it goes down into a groove like that. What that does is that prevents, if this were to explode internally, that prevents that arc flash, as it's known, to come out through the sides. It makes a nice strong container that it can't get out of. You don't want it to get around the sides and burn your hand, which is going to be on it. So we'll take it apart here. And let's take a look here. Sorry, that's blurry. I know. Alright. So what you have are these big Hrc fuses. That's high rupture capacity. And that's what you want. These are generally ceramic, fiberglass with potentially a sand fill inside of it that prevents them from rupturing if you're many times over the short circuit current rating of these fuses. Because a fuse like this, let's say one of them I believe is probably rated for 11 amps for the 10 amp current jack. Well, at 11 amps, it's going to blow after a very long period of time. We're talking seconds. if you're twice the current, say 22 amps, then it's going to blow in, a matter of milliseconds. And as you increase in the number of amps, the number of times past its current rating, its rating that it blows at, then it blows faster. But there comes a point where this fuse has what's called a SCCR rating, short circuit current rating. And what that means is you can actually get to a current that's so high that this thing either arcs over and doesn't become an open anymore, or what more likely will happen, and dangerously so, this fuse will just rupture. It'll explode, it'll blow particles all over the place. So these are important to have. They have the little glass fuses. You notice the other one didn't have any fuses, although it didn't have a current jack. It had the clamp, so it wouldn't need it. But a meter like that would normally have those little glass fuses you're probably used to seeing, the little 3AG type fuses. So this is good. And then all of this is covered in another layer of plastic, and there's this piece of plastic here that separates your two, your 400 milliamp, 400 milliamp, and your 10 amp fuses, respectively, just to kind of make those distances bigger. Let me get this plastic off, and we'll take another closer look at the board. I just want to take a moment to appreciate some of the niceties of the Fluke meter versus this piece of junk here. Look how nice the board is. You can just tell the quality. It just exudes quality compared to this one. Maybe it's hard to tell unless you get a microscope out and look at the vias and see how good the registration is on the vias, how good the plating through is. But just looking at the surface, this just looks like a quality board. It looks much nicer. It's all fully routed on the outside. This is all V-groove and snapped off for mass production. It has the gold plating on the pads there. It's just really, really nice construction. And a good meter will have shielding on the inside too. This prevents any noise, external noise, interrupting your measurements. In an industrial environment, that's a really important thing to have. Before I take this fully apart, I just wanted to show you this piece of plastic here is actually from that front plastic cover, and it comes all the way through a slot in the board there. So that not only physically with the plastic has a blast protection layer, but also it prevents any surface creepage on the board. It needs to go all the way around that piece of plastic. And air has a very high insulation, so you would need a lot of voltage to be able to overcome and go around that. It's very unlikely that that would happen. And just look at these input jacks. On the front here, you can see that they're solid. I don't know if they're machined pieces of metal. They may not be thick enough to actually be machined. They might be molded, but they're solid pieces. They're not split like the other. And they're actually soldered right onto the board, it's a pretty robust technique. A little bit better than the flimsy little pieces of foil that we had coming over on the other meter. Alright, let's open this thing up, see what we've got. Whoa! So, a few things to point out here. You'll notice that over here we have, I can't tell if that would be a PTC. It's a positive temperature coefficient. I think that probably is what's known as a thermistor. So as current would go through there, if there were an overload condition, the resistance would rise as this heats up due to that excess current, and would actually lower the current coming through to help protect the meter. Then you have this giant resistor here. Now, the point of this resistor isn't that you need a huge amount, let me zoom in, a huge amount of power handling ability. Chances are you don't. That's not the real issue here. The issue is, look at the huge space between this terminal and this terminal over here. That gives you that distance, that breakdown distance, to use air to prevent any arc over, because that high resistance of air. That again protects you. If this were to try to rupture, it wouldn't be able to arc over. And you notice they've put some S&D resistors. They look like maybe 0805 resistor packages in series like that. Again, the reason isn't that they couldn't get the resistor value that they wanted, and so they've just put a bunch in series. The reason is to give you that huge space where you have that protection. Then moving along the line here, you've got MOVs, metal oxide varistors, where if they reach a certain preset voltage, whatever they're set to, let's see if I can see what they are. It's not listed on it, but it would reach that preset point, and probably they have one going across the line, and then one going from each terminal to ground or something like that. They usually have them in different configurations. And what that would do is it would basically clamp the voltage. It wouldn't allow it to go any higher. And if it did, these would start to heat up. Now these will explode. If you continue to overload these things, they will just rupture. But that's okay, because they're going to take the brunt of that rather than, just sending it out into the atmosphere and exploding. So there's your input protection over here just on one side. That is a huge amount of protection, and you can see it goes right around the battery case. So the separation distances between, well, let me look at, where's the front? Yeah, so the separation distances that you have between those is huge. And you of course have your current jacks over here where you have that nice isolation slot where the plastic came through. There's your 10 amp current shunt there, and the diode bridge there is not actually to rectify that. That's actually there again for clamping. So if your current, or I'm sorry, well, yeah, the current that's going through this shunt is higher than a certain value, and it goes above and beyond what your fuse can handle, but is still conducting for a certain period of time. Because remember, these are slow blow fuses. They take time to blow. For those really quick instantaneous overloads on your current range, these diodes, they have that 0.6 volt drop across them, will clamp the voltage across this shunt to no more than whatever the total combined voltage drop of those diodes are. And again, same situation here with your big resistor. Chances are you don't need that big resistor. It's to get that separation distance. So you can see on all of the ranges here, you have a huge amount of protection. A meter like this, I would have no problem putting it on the ohms range and then plugging it into the wall. I'm not going to do that because that could destroy the meter potentially. It probably wouldn't, but this is an expensive meter and I don't want to put my own meter at risk. Although, from my life perspective, I don't feel that there'd be any dangerous. I don't feel that that would be dangerous, and I wouldn't have any qualms about that at all. So I just wanted to show you the stark differences between a really high quality industrial safe meter and the cheaper unsafe meter. If you're going to be taking measurements on any kind of industrial scale whatsoever, please do yourself a favor and get something designed that's quality. I can see here you've got a Fairchild chip. This looks like, what is that, a TI part, probably an MSP 430 variant. Linear Technologies with the Fluke branding on it, and other Linear Technologies. This might be the True RMS chip, because it is a True RMS multimeter. That's probably your, one of these will be your voltage reference, maybe that, because I don't think you'd need that many terminals. I'm not going to go through it. Maybe I'll do a teardown of this another time, and we'll look in more detail and see what everything is and how it works. But for now, I'll leave it at that. And if you have any questions or any comments, just leave it on the comment section. Don't forget to like the video, and if you haven't done so yet, please subscribe. Thanks, and we'll see you again. Wait! Moment of truth! Does it still work? Yeah.